So we're going to begin looking at Chapter 5 now, static equilibrium for rigid bodies. And so we have a box here. So we're just going to start with the problem. The basic equations are sum of forces equals 0 and sum of moments at any point you want to choose equals 0 for static equilibrium. So we have a box here. It's 1 meter by 1 meter. All right. There's friction here between the box and the floor. Static friction is 0.6. Box weighs 600 newtons, and there's a 300 newton force being applied at this top corner here. And the question is the box still? So there's two kinds of motions we could have. It could slide, or it could tip. So we have to. These are very classic problems known as tipping or slipping problems, or none of the above, that we gotta consider. All right, so if I look at this thing, the first thing we need to do always is the free body diagram, which I put here. And notice that I put the normal force out here, basically approaching this corner. Why would I do that? Okay, as you push on this box, the effective that's going to cause this box to start to lean, and so the normal force is going to be going from the center and start moving out. Now here's the thing: if the normal force effectively will move as far out as it needs to counteract the tendency to want to flip. So if we look at this thing relative to this corner. So you have the weight of the box would tend to take it counterclockwise, but this force here, relative to this point where it would tip, wants to take it clockwise. Now, this normal, as this would move out further and further and further this way, provides an additional counterclockwise opposition. Here's the thing. If the normal force has to go outside of that corner to stabilize the box, that gives you a clue. It's tipping. It's going to be tipping. Now, in case this kind of bothers you, seeing me move the normal force out the side, I would just make a little comment that I took my elder son one year to New York City, sort of as a reward for some things he had accomplished, and so we went down there, and we went to the Statue of Liberty, and we went to some museums. We went to the Empire State Building. The World Trade Center was gone by this point. And we went to a Yankees game, and well, we just had a great time. Anyway, so I took him down on the subway, and one of the games on the subway. So if we could. If you can try to picture this, so just add a little picture in here. So subway cars aren't very long, and actually compared to, like if you see Via Rail, those cars are 85 feet long. Subway cars, I don't know, maybe 40 feet or something. I don't know exactly, but they're a lot shorter. And that allows them to turn, because if you look at the city streets above, so like here's a street, the line below the street, so you have these rail cars going, and if the tunnel has a right turn in it, or maybe there's a switch here so it could go straight or turn, at full speed, they make a turn, all right? It's kind of fun to ride on these things. So they're shorter in length, so that allows them to turn on a tighter radius, quote-unquote, safely. So here's the game, that if you go into one of these cars, there's these hooks hanging down, and so one of the games you can do with somebody is you go and you don't hold on to a handle. Rather than taking a seat, you try to see. The other thing we need to point out, these cars, they're all electric, so there's a third rail by the rails that support the car, and then they have a contact, and that drives motors that are in the wheels. All right. So this is pure electricity. They get really high torque, so the acceleration out of these things is incredible. Plus you have these hairpin turns that can happen. And so it's a really neat game to be riding on the subway. And So you can have this contest to see who can stand up without having to grab the grab bars above or a seat or whatever to hold your balance. So if I draw a bigger person here, all right, so you're standing there, and let's let the rail car is going this direction, all right? And so what's going to happen is that wants to flip you over this way, and so as the car starts to speed up, what you do is you wind up putting more weight here, pushing down near the backside. You start to lean, you put more weight in the backside, so that's basically relative to your center. That force down there is providing a torque the other way to keep you from falling over. So as this thing speeds up, you start to lean, all right, to counteract the fact that the train's literally trying to flip you over. So the same idea here. If somebody's pushing on this, box will start to have a lean, and the normal force will move further and further out. If the normal force has to go so far out that it's outside of the box, that means there's not enough there, the box is going to flip. All right, so that's why I did that the way I did. So let's just start. If we look at this, if we sum the forces in the y of 600 newtons down and the normal force, these ends are different, going up. It's very clear that N is 600 newtons. Now, here I have static friction. Now keep in mind, static friction is lazy. This determines the maximum amount of static friction available, okay? And there's only as much as you need, okay? So if we look at this thing, given that N is 600, so force of friction max for the static case, so F max is mu s times N, which would be 0.6 times 600 is 360. So if we look at that, we can go, okay, 300 this way, 360 is available going the other way. It'll only give the 300 that's needed to oppose that, but what we see is there's a spare 60 sitting here. So we are not even close to slipping. The question is where are we relative to tipping? So what we need to do is figure out where exactly is this N here. So let's add to our little drawing this distance here, X. And we're going to figure out where that is. All right, so here's what I'm going to do. Here's G in the center of the box. So I'm going to sum the moments at G, and they need to be 0, because if it's not, it's a tipping. So let's figure out what we have. So this 300, this is a 1 by 1 meter box. So this is a half, the perpendicular distance to G is half a meter. So I have, going clockwise, 300 times 0.5. Knock that off. So let's see. Force of friction will just equal that. So that's also going to tend to want to make us go in the same way. So that's another minus 300 times 0.5. Then I got this 600. The weight goes through G, so it doesn't exert a moment. And so I'm left with this piece here. So N, we figured that's 600, and it's going back the other way. So plus 600 times X. And the question is how much X is there? And so if we look at this, X equals 0.5. So what that's telling us is the normal force is right on the edge. If we were at 301 newtons, this thing would tip over. So we are on the, so it says determine the static equilibrium. It is at equilibrium, but it's on the edge of tipping. So there's that one. Now we're going to kind of move on to just explaining a concept. And one of the common things we deal with are what are called two-force members. And two-force members are massless. And so what you have is they tend to be rods. And we treat them as massless, okay? So relative to the forces going through them, they don't weigh very much. So we just ignore the weight that they have. So for a two-force member, so basically picture you have a connection point here and a connection point there. And so if you were to isolate the members, you'd have a force applied here and a force applied there. And the question that I want to ask you is, what are the conditions for a two-force member to be in static equilibrium? And if you just try to draw some pictures, first of all, we need the sum of forces to equal 0 and the sum of moments to equal 0. So there's only two forces, there's no weight. So if I had two-force member, means you can have a force here, and we can say put a force there. F1, F2. If I sum forces along this direction, this one, even if the back of this can oppose that, this one, the y component of this force, this one can't oppose. So that won't work. All right. Let's try this combination. Suppose we didn't have that. So I have that force here. And suppose at the very same angle, I put that one in there. So these are parallel. All right. So if we look at this, these are the sum of the forces here will be 0. So what we're seeing here is, for the given only two forces, the forces need to be aligned and opposite in direction. Otherwise, the sum of forces won't be 0. But notice for what I did here, if this one goes here and that one goes there, we have a nice perpendicular moment arm relative to these. This is a couple. This is going to spin, tip, rotate, whatever you want to call it. All right? So we don't have the moments being 0. Here's the bottom line. The only way a two-force member can be stable is if the forces are equal, opposite, parallel, and collinear on a line. That is the only way this can be stable. All right? Well, that gives us some information we can possibly use. So suppose you're given a structure where you have a two-force member, where you know already that the system is stable and you're just trying to figure out the forces going through. All right, so you know it's stable and you want to find the forces going through the member. Well, if you have a two-force member, you know the forces go on a line between the connections. The connection here, the connection there. The forces are absolutely on a line. So this is the two-force member. We're going to take a look now at the three-force member. All right, so so picture here I have the quote-unquote member, and I'm just showing that as, so there's connections here where forces are. And so this is a member that's often massless. If it's not massless, then the weight is one of the three forces. Okay, so we have three forces, one of which may be weight. And so suppose you have a member that is in static equilibrium. So you know it's in static equilibrium. What does that tell you about the forces? Well, if it is in static equilibrium, the following must be true. The sum of all the forces in every direction are 0. And the sum of the moments at any point you choose must be 0. Well, let's think about this. So here I have a member, and there's two forces. And if I continue, one force comes in here, one force comes in here, and if I continue a line through, there's a spot where they intersect. All right? And so here's the third force, so-called F2. What can you tell me about that force? Well, they would have to sum up to be 0, but their moments would be 0. And so here's the thing. I'm going to draw 3 possible F2s. So here's an F2, one here. Here's one here. There's one there. Of these three, which one must be the F2? And the answer is it has to be this one. Because if these two point to the same spot, I'll call this O, all right, that means this and that have no moment relative to that spot. If that means this force has to go through that line, through O. Otherwise, if it doesn't, there will be a perpendicular distance associated with it. And that would mean there's a moment, non-zero moment, and therefore this thing is spinning. So if you have a three-force member and you know that it's already in static equilibrium, it means the three forces, if the forces aren't all parallel, I'll deal with that exception in a minute, but if the three forces aren't parallel, you must be able to find a point where they all point to, that they have in common. Because if they don't all point to a given point, then you're going to have a moment. You have to. All right? So how can you use that? If you know you already have static equilibrium, and let's say you know two forces, well, that tells you the direction of the other force. These two, where do they connect? Oh, they connect here. Well, this third one, if you know it's the forces happening at that point, you know it's on a line from here to here. And then, knowing this, knowing that, you also know the magnitude of the force, because all of these things have to balance out. So this is a tremendous amount of information. If you have a three-force member and it is in static equilibrium, the forces all must meet at one point so that you have zero moment. Now this is the case where the forces aren't parallel. So the alternative is the following down here. So this is the case, these are all parallel, so you would have to have the sum of the forces. The sum of the forces would have to be 0, and that's easily done. This, that, and that can add up such that it's 0. And when we say the sum of the moments are 0, just like before, they're parallel, so that means they meet at infinity. Okay? So if you have two forces that are parallel and you have static equilibrium, it means this one is parallel to the other two. And then you can just use your equations to figure out what that is. All right? So if I have these two that are parallel, and there's a third force, the only way this thing is in static equilibrium, if this is parallel to the other ones, where they all meet at infinity. Then you still have to be concerned with the magnitude of that force, that it balances everything out. Okay? So this, when you observe you have a two-force member or a three-force member, you can use this to your benefit in solving problems. There's information here that you have that you can benefit from. All right, the rest of the way out, we're going to start solving problems. I'll catch you soon.